So today we're going to start doing derivatives of exponential functions, and it's probably good that we know the behaviors of exponential functions before we start finding derivatives on them. An exponential function is when x is the exponent. Okay, so you'll have base to the x. Now, if the base, these are really important to discriminate between the two types of graph. If the base is greater than 1, you will have this type of graph. Okay? As you go to negative infinity, this is negative infinity this way, you will get closer and closer to 0. You won't ever get to 0, but you will approach it. And as b goes to positive infinity, you will see that the graph goes to positive infinity. And the domain would be, actually we can do domain and range after we're done both of them. Now, when you are doing a fraction, or anything like a proper fraction, impropers are when the top is bigger than the bottom. That's going to be case 1. But when you have a fraction where the top is smaller than the bottom, okay, which is called a proper fraction, or a decimal, 0.8 less than 1, you will get basically a reflection on the y-axis. And that will have kind of opposite limits, because as we go to negative infinity, this graph goes to infinity. And as we go to positive infinity, this goes to 0. Now, one thing you have to know is the base is always positive. If you have a negative base, like example y equals negative 2 to the x, what you do is you get your points. See, when, say, x is 1, right, that would give you negative 2. When x is 2, it's going to give you like positive 4, right? So your points jump all over the place because your base is negative, right? Every even power or exponent will give you a positive, and every negative or odd power will give you a negative, right? So that's why it doesn't give you a nice flow, doesn't give you a nice graph. Now, even though they are different graphs, they will have the same domain, x in the reals, and the range, y is greater than 0. Not greater or equal to, but greater. So what would be the graph of y equals 0.9 to the infinity, or to x? Now, got to remember, this is what that graph looks like. So as we go to infinity, this will approach 0. Okay, now 3 to the negative x. Now 3 to the negative x, just to kind of, this is the same thing as limit x goes to infinity of 1 over 3 to the x. So now we're dealing with a base between 0 and 1, right? Which is again going to give us our graph like this. So this will approach 0 as well. Now, limit as 4 to the 1 over x. Now, this one you want to think about. What happens if you put infinity into x? What does the exponent become? So this will approach 4 to the 0, right? Which equals 1. And again, you can test your values by putting in numbers bigger and bigger and bigger and bigger, okay? And just on that note, yesterday we found out that one of the questions on your test some calculators, if you were to put in a really, really small number, like 0.000001, your calculator was rounding that to 0 and then plugging that into the limit that you did. So some of you were getting 0. And some of you were getting 0.167. Is that the right the other, right? If you had a different calculator, okay? So what I did is I counted 0 and, so that was A and B for that one, right? So that that helped all of you pretty well. So I gave our class average another 2% on top of that. So just to prove that, I said that because you guys were saying that the trig unit was harder, you did get 6% average higher than on the applications test. So if it is harder, results don't show that it's harder, and results are everything. So. Whatever it was, results were better, and I'm all about results. Oh yeah, we're gonna skip that one right now. I think we've had enough trig for a while. Except we will do a little bit in a bit. Okay, now we're gonna actually we just touch on this in 30-1, but today we're gonna and tomorrow we're gonna get much more into detail. Now, if we try to find the derivative of b of x. Now, if you remember, the derivative formula is this here. And if we're going to use b to the x, well, then we put the x plus h minus b to the x all over h. Now, using your laws of powers, we can split that up into b of h times b, or b of x times b of h. And you see that now that we have a b of x in both, do you guys not have this? Okay. H approaches 0. Okay, so want to write this down then? I'll slow down a bit. Anything to stop the whining. Okay, and just as you're copying that down, see if you have any, going through anything that you're like, what? How'd they do that? This doesn't make sense. And because b to the x has nothing to do with h, we can bring that right out front, and that's at very bottom there. So the limit now becomes b to the h minus 1 over h. And if you put in 0, you're still going to get undefined. But okay, now, since the b to the, now this is saying, hey, if you put in any b, you can use this, right? So the derivative of b to the x will be b to the x times the limit. Now, there is a, like we want to know, well, okay, so we are left with this still. What happens if we start putting in numbers closer and closer to 0. Now, if we use the base 2, right, this, and I'm not going to go through the whole process, but it gets closer and closer to 0.69. Now, if you put 3 in there, and again, you put in 0.001, it gets closer to 1.09. So there is a number, actually, that there is an exponent out there, or a power, I should say, that if you put it into this formula, you get the answer 1. And obviously, it's going to be between 2 and 3. Okay? And the number that actually gives you the answer 1 is 2.71828. If that's your base, then the derivative of, okay, I want you to, because remember, it's b to the x times, as h goes to 0, oops, limit, b to the h minus 1 over h. And if you go and put 2.7, let's just go 2.72 to the x times limit, h goes to 0, of 2.72 to the h minus 1 all over h. This will be 2.72 x times 1, which equals 2.72x. So it is the only number in the, or only power in the world that the derivative of it is itself. And that number is, it's not 2.71828, it's 2.7128, blah, 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 it goes on forever. And it is given the number, the letter E. So it is the only base that the derivative of it is itself. No other number works. 2 doesn't work, 3 doesn't work, 2.7 doesn't work, 2.8 doesn't work, just 2 point, and that's how he discovered it. And it is given the letter E because Euler is his name, okay? So Euler. Okay, so he's a Swiss mathematician. He's the one that introduced, he did lots of things. He introduced the f of x notation. That was his, yeah, he's to blame. He introduced, this will even make you more happy, sine theta, cos theta, tan theta. Yeah. He didn't actually come up with the ratios, he came up with the names. Okay? That's his babies. Yeah, well, it's, you know, advertising is everything. Okay? The letter E, obviously, is his. Yeah. He made up this symbol, the sum, and the I for like imaginary numbers, and then probably one of his most popular, the pi sign. Yeah, he's like, so someone did all the work and came up with the number, and he's like, he got it in there fast enough, right? He's the one that he did the patented. Yeah, a little bit of an opportunist, I think he is, but rich opportunist probably. Because every time you use the word pi, he gets a little bit of kickback on that. But you didn't even know that. Don't you see the little TM on top of the pi sign? If you look good enough, it's there. In fact, we could be sued by not having that in there. Okay, so this is the graph of e to the x. This is y e to the x. And what's cool when you look at the graph even, do you see that if you did the derivative of this graph, you get the same graph because the slopes, that's the graph of the slopes, and the slopes actually equal the y values of the original graph. Yes. Should I just press pause? Okay, so the y values of y equals e to the x equal the slope values of the y values of y equals e to the x equal the slope values of y prime equals e to the x. Don't worry, Simone, I'll get the door for you. That's not coming in here. Yep. Okay. So, everybody got that? So let's turn the page. A little Bob Seger song there for you. So d over dx of e to the x is e to the x. So the y values of the original equal, yeah, there should be, equal the slope of the new graph. Okay? Just one thing to further add though, the derivative of e to the u is e to the u du over dx. Okay? That's if exponent is not an x, it's a 3x or it's 3a or whatever, you've got to do the, okay? So we're just going to spend the rest of today just doing examples. There's 8 on here, but then I have 3 more that are going to help you with your homework. Okay? So, everyone got their formula sheet out? Because that should be on there. Finding your formula for e to the x is e to the x, or e to the u du. Okay, so these are the ones we're going to be working on today and tomorrow. So, third page, there's the very first one. Okay? So, very, very top there, blue ones. So maybe let's rewrite this as y equals e x to the 1/2. So the derivative of it will be y prime equals ex to the 1/2. So that will stay the same. And then we do the derivative of the exponent, which is 1/2 e to the negative 1/2, which would give me a final answer of e to the square root x all over 2 square root e. Or square. Sorry, that shouldn't. Sorry. Okay. That's supposed to be the derivative of the exponent. Okay, so always do the derivative of e to the exponent, write that one more time, times the derivative of just the exponent. And then you want to clean everything up. In number 6, we would be using what rule? Product rule. So let's do dy over dx. We haven't used that notation for a while. Let's go x to the 4th times the derivative of the second, which would be e to the x, plus derivative of the first, 4x cubed, e to the x. Okay, now we just want to clean it up at this stage. Each one has an x cubed and an e to the x. So I'm going to take an x cubed out of both and an e to the x out of both, leaving me with x plus 4. Okay, the next two, we're going to do a little trig. What was the derivative of tan u? So then we would use secant squared u, which is e to the x, times the derivative of the inside would be e to the x. Okay, so y prime, we always put the numbers in front usually, because e is a number, right? Secant squared e to the x. Oops, e to the x. Okay, this one we're going to have to use the product rule again. So y prime equals, we've got the first times the derivative of the second. So we would first do e cotan 4x, right? Because that's a derivative. It almost looks like we left it alone, but we did do the derivative of it. Now I'm going to do the derivative of the exponent, which is negative cosecant squared 4x times 4, right? We still have to keep doing that derivative of the inside. So you can put this all in brackets, because that really is all together, plus the derivative of the first, which is 1 e to the cotan 4x. Okay, now if we can take out a, I don't know, what would be a good way to clean this one up? Yeah, we can take out an e cotan 4x. Oops. E cotan 4x out of both. Now, remember, this entire thing is like one thing multiplied together, right? And we didn't kind of clean it up first, but we could probably use our imagination here. That would leave me in this one with a 4x cosecant. Oh yeah, we actually, if we take out a negative e, we would leave this as a positive, but it doesn't matter. But it's good to just see it in a different form, so you can match it to multiple choice if you had to. -1. Okay, so I just want to do 3 more. I went through the homework and I thought these examples aren't really going to prepare you for the homework, so let's do this one here, y equals e to the 3x over x cubed. And we are always moving these to to product law by making that x to negative 3, but let's just practice our quotient law, because obviously if we don't, then you're going to have to feel like you're doing more studying for the final exam because you haven't done it forever. So we'll do y prime equals, so what's low, right, d high, which would be e to the 3x times 3, right? So low d high minus high e to the 3x. D low would be 3x squared all over x to the 6. And then y prime, we can clean up the top by taking a 3x squared out of both and an e to the 3x out of both. Leave me with x minus 1 all over x to the 6. And instead of rewriting the whole thing again, we can cancel out some x's. This would be gone, and this would turn into a 4. Okay, let's just do one more. So let's do number 10 here is y equals e to the 5x times 2x minus 3 to the 4. So these aren't any more difficult than the ones you've done before. It's just review. So y prime, we can do first times the derivative. So first is e to the 5x times the derivative of the, oh no, let's do derivative first times second. So derivative first is e to the 5x times 5, all times 2x minus 3 to the 4, plus e to the 5x times the derivative of the second, which would be 4 times 2x minus 3 to the third times 2. Okay, we can take out Can we take out an x? No, we can't take out an x. We can take out an, oh, e to the 5x. Yeah, let's take out an 5 e to the 5x. That would leave me, and a, oh, what else? We can also take out a 2x minus 3 to the 3. Oh, no. Okay, yeah, you're right. I can't take that out. Yeah, yep. No. So that, then I would be left with 5 times 2x minus 3 plus 8, because the 4 and the 2 were left behind. And then I can now just tidy that up a bit. E to the 5x times 2x minus 3 to the third. Now that would be 10x minus 3 plus 8. Or 10x minus 15 plus 8. 10x minus 7. No, oh, sorry. Y prime. No second derivatives today. Okay, so the only difference I want to make to the homework is for number 1, just do A, just because it's Friday and I like you guys. Wouldn't do this for any other class, just so you know.